Hi everyone. In the previous lecture, I have shown you that how we optimize the geometry of the antenna so that it may operate on our desired frequency. So in this lecture, I will teach you some further knowledge. I will give you some further knowledge about voltage standing wave ratio. So the voltage standing wave ratio is the voltage signal which propagates through the feed line, and when if there is a mismatch, some portion of that signal reflect back, which creates some standing waves. So we call that voltage standing wave ratio, and it should always be less than 2. So the voltage standing wave ratio is an indication of the amount of mismatch between the antenna and the feed line connected to it. So if its value is high, it means that more of the signal is reflected back. So if you look into this antenna, you may see that we have a feed line here. So this is our antenna, and here we have a feed line. So this is the feed line, and the voltage standing wave ratio values can range from 1 to infinity, but the voltage standing wave ratio under 2 is most suitable for antenna application. The antenna is described to have a good match when it is less than 2. Now the voltage standing wave ratio depends upon the reflection coefficient. Voltage standing wave ratio is a function of reflection coefficient which describes the power reflected from the antenna. The reflected coefficient is given by gamma. So if gamma represents the reflection coefficient, then the voltage standing wave ratio can be represented with the following formula. Voltage standing wave ratio is equals to 1 plus absolute or modulus of the gamma divided by 1 minus absolute value of the reflection coefficient. So here we have a table which shows the VSWR values, or the voltage standing wave ratio, against the return loss. So if we have VSWR 1, the return loss would be 0, but in dB it would be infinity. If we have a VSWR 1.1, the return loss would be 0.0454, and in dB it would be minus 26.3.848, which is considered as the best VSWR value, or the best return loss value. If we increase the standing wave ratio, then on the other side in dB about the return loss, we can see that the value is decreasing, or it is shifting towards positive axis, or it is shifting toward the positive values. So the lower value of the return loss in dB represent the perfect match between the feed line and the antenna. So the value 2 is considered as best, or any value under 2 of the voltage standing wave ratio is considered as better. So in return loss in dB, if we look into it, it is minus 9.52. If any return loss is of the antenna is below minus 9.54 dB, then it would be considered as the best match between the feed line and the antenna. So any VSWR of any antenna which is less than 2, it is considered as the best match, or the more efficient antenna. So now we will go into our antenna. This is our geometry which we have designed in the previous lectures. Now I will show you that what is the voltage standing wave ratio of this antenna. So we will go to the 1D result, and here you will see a folder which shows the VSWR. If I open it, you can see here we have a voltage standing wave ratio plot here, which is ranging from 10 GHz to 15 GHz. But our antenna is at 13 GHz, operating at 13 GHz. So I will draw axis marker, and I will draw it at 13 GHz. So first I will draw the marker. So I'm going to show axis marker. So you can see this is the axis marker. Now I will drag it to 13 GHz. So if I drag it into rightwards, so here you can see it is at 13.00011. I will write 13 here, Click on OK. Now it is in 13 gigahertz. So at 13 gigahertz, I get 1.1967588. This is the VSWR value. So if I go to the table, you can see that at 1.1, we have a minus 26.848 return loss, which is the best one. So this is a very efficient antenna. So if I want to plot both of the reflection coefficient and VSWR on single plot, so I will go to the S11 and you can see that both of them is visible on a single plot. So the reflection coefficient value at 13 gigahertz is ranging slightly below minus 20.